Okay, let's get started. Motion planning, lecture number 5. Today our topic will be PRMs, probabilistic roadmaps. And before I go into details, I just want to give you again a broader overview of where we are in the lecture right now. So as I said, lecture number 5. So in the beginning we had one lecture by Wolfgang where he talked a little bit about, gave you a little introduction into motion planning, and then I had one lecture just about the configuration space, how it looks like, how you can construct it, how you can put distance functions on it. And then we had 2 lectures by Wolfgang about search-based planning, which I would say is the first basic approach you can do to solve motion planning problems. And I would say this is not the most commonly used approach for motion planning, but as you will see later on, a lot of those tools which you have developed there, like this A-star algorithm and admissible heuristics, they are super important also for other algorithms. And so I think this is really something you should know so that you can appreciate some of the algorithms which are coming up. And now we will go into the second phase where we'll talk about sampling-based approaches to motion planning. And I would say sampling-based approaches are really the state of the art for motion planning. They are really the ones which can solve very high-dimensional state spaces. And so 2 very famous algorithms are RT and PRM, and today we will talk about PRM. And I think next week we will talk about RT. Those are basically the 2 big approaches to motion planning, and they work very well, and I think they are the ones which scale best in the number of dimensions to higher dimensional state spaces. Okay, and then the next 2 topics will be optimization-based planning and also some advanced topics. We will go a little bit into machine learning and also multi-robot motion planning approaches. Okay, this is again small recap. Today, as I said, will be all about probabilistic roadmaps, which are really one of the major approaches to motion planning. And the idea is basically pretty simple. So the idea is just that you sample random points in your configuration space. And once you have sampled random points, you try to connect them to each other. And so this looks like that. So you just sample randomly in your configuration space, you get some points which are valid, you store them, and then in the next phase you try to connect all of them together so that you get a graph. And this graph we usually call a roadmap. And this roadmap basically gives you a representation of the configuration space, and then you can use this representation of the configuration space to plan motions to go from any point A to point B. And this idea was first published in 1996 by Lydia Kavraki. She's a professor at Rice University in Houston, Texas. The basic idea is that we have 2 steps here for this algorithm. The first step is that we have some pre-processing. This is actually what I told you, this creation of this roadmap, where we have basically the environment and the robot. We sample random positions, random configurations. We try to connect them and get this roadmap. And then in the second stage, we have a query phase where you are given a start and a goal, and you try to exploit the roadmap which you have constructed in the first step to actually find a path by doing a graph search on this roadmap. So the initial idea, very simple. And something which is pretty cool about this probabilistic roadmap is that you can reuse it if you have different start and goals. So if you have an environment which is not changing, if all your obstacles here are static, if your robot doesn't change, then you can use this probabilistic roadmap as a multi-query planner, which means given a start and a goal, you don't need to recompute this roadmap again, but you can reuse this roadmap to compute another motion. And so this makes it pretty efficient for those cases. Of course, if you have dynamic obstacles, if your robot changes, then you can't use it anymore, but this is a very nice property to have. Yeah, and so I want to go a little bit more into detail how this actually works. So this is the pseudocode of this probabilistic roadmap. As input, you get a configuration space, you get a free workspace, you get this B function, which is the function which maps a configuration of the robot into the workspace, and you have a number n, which is the number of random configurations you want to sample. And then, as I said, there are two steps here. In the first step, you generate n vertices. So basically, you just iterate here. You sample a point from your configuration space. And then you check if your robot is actually collision-free. And if it is collision-free, bless you, then you add the configuration to your graph here. So the graph is represented as G, and it has some vertices V and E. And so once you have actually sampled some configurations, you go to the next phase where you connect the vertices. So basically what you do is that you iterate over all configurations on your graph. So those are all the valid configurations which you sampled. You compute neighbors of those configurations. And then you check for each neighbor if a path exists from your point to your neighbor. And if there's a path, then you add this path to your edges. And this basically creates you this roadmap. And then you return the roadmap. And then you can do queries on the roadmap, as we will see shortly. OK. And so, yeah, here again, small presentation of some configuration samples. So you can see here this is a point robot on a 2D grid. And there, yeah, if you just sample randomly, you get usually some points here. And then you can use them to connect actually to this roadmap. OK. And so now the question is, of course, how can you exploit this roadmap to compute motions once you have a start and a goal configuration? And so the general recipe for that is given here. So what you do is that, let's say you have Q start and Q goal. Those are start and goal configuration of where you want to go with your robot. What you do is that you add those two configurations to your roadmap. Then you try to connect start and goal to at least one vertex of your roadmap. And then you try to find the shortest path on the roadmap. And you can use a star, which we had in the last lectures, to just find a path. And you can see this here schematically on the right. So you have here a point, which could be Q start, and you have a point here, Q goal. And then in the first step, you try to connect them to the nearest neighbor on this graph. So for example, that would be this point here for this configuration. And for this configuration, it might be this point here. And then once you have connected them to the graph, you just do a star search on it. You find the shortest path here, which you're guaranteed to find with a star. And then you are done. And one important question is, of course, what constitutes actually a good roadmap? So of course, we don't want any roadmap. We want a roadmap which has certain properties so that we can actually use them for planning. And one big property, I would say, is the one of accessibility, which means that for any configuration in the configuration space, in the free configuration space, we can always compute a path to some vertex in our roadmap. So that means the roadmap needs to be dense enough so that we can always find at least one point which is visible from any configuration in your configuration space. The second is, of course, that it should be also departable. So this is basically the same idea, but of course for your goal configuration. So the reason why we have two properties here is because in the one case we go from a configuration to the roadmap, in the other one we go from the roadmap to the configuration. And often this doesn't matter, but sometimes we have special constraints or special metrics, and then this actually does matter. So that is why it is important to make a distinction here. Then we also want it to be connectivity preserving. So whenever we have two configurations which can be connected in the free configuration space, then there should be, of course, also a path in the roadmap. That basically just means that every clusters of points are always connected if there's actually connection. And that comes, of course, on top of this accessibility, so that we can always be sure that there's also a path on the roadmap. Okay, and then it should also be efficient. Usually we have like an epsilon factor, so that we say whenever we have two configurations which are connectable with a certain cost C star, then we want to be sure that in the roadmap there's actually a path which has the cost of epsilon times C star or less. So that basically just means that the roadmap should be, kind of, in a sense, optimal, so that we don't find, some weird paths or some very long paths, but some paths which can keep us in a certain limit, so that we are near optimal for a certain factor. And then, of course, on top of all those properties, we also want this roadmap to be sparse, so that we can save on memory. We want to have very few vertices and edges, but we want them in such a way that they're still allowing us to keep those properties here. And so I would say this is really one long-term goal, to have really a sparse roadmap which represents the configuration space as best as possible, while still keeping guarantees like being efficient with some epsilon, and also always being accessible from everywhere. Okay, so that is basically the ideal case we want to go to. And now I want to analyze a little bit how we can actually get there. When is actually a roadmap accessible, departable, connectivity preserving, efficient, and sparse? So let's look at some, I would say, edge cases, namely the cases where we take n and let n go to infinity, and then I want to also look at the case where n goes to 0. So for the case where n goes to infinity, the cool thing is that there will usually always be a configuration on your roadmap for every configuration in the free configuration space, which kind of makes sense because we have just densely sampled and we have gone to infinity with our number of samples, so that should be always a point very close to any point in our configuration space. And that actually makes it accessible because now we are very close to any given point in our configuration space. Of course, it's also departable, and it would also be connectivity preserving. So you can basically always go from one point to another by just making very small moves along the configurations which you have sampled. And in the same sense, it's also efficient because you have, of course, such a broad array of configurations, so that you can always also represent the optimal paths then. Of course, if you have a lot of configurations, then this roadmap will not be sparse. And the computations on them will be very slow. This is true, of course, both for pre-processing, but also for querying. Running a star on a very, very dense roadmap will, of course, take a lot of time and will not be super efficient. Hey. No problem. Okay, and the other edge case would be where n goes to 0. Then, of course, almost no configurations or almost 0 configurations. This will not be accessible, not departable, not connectivity preserving, not efficient, but it will be very sparse. And the more you go actually to 0, the sparser becomes this roadmap. So you have to always have this trade-off between having all the nice properties of being accessible, connectivity preserving, efficient, but you have to always trade it off with also being sparse, being memory efficient, and also, in this case, being efficient at actually solving a new query. So the less points you have, the faster will be also your query, which you compute at the end. Okay, so this is a little bit for analyzing the roadmap and the number of points. Yeah, now some practical considerations. So one thing which you can actually do to speed everything up is that you pre-process the roadmap and you query in parallel. So which means that you incrementally increase the roadmap size and you periodically check if a solution can be found. And this is a nice way because now you actually avoid picking in explicitly. So usually how this actually works in practice is that you sample a point, you check if this is already enough to find a path for your problem. Then you sample another point, you check again, and so on and so on. And at some point you will be at a certain number of points, you will have found a path, and then you can already say, okay, at least I have a solution now, and now it's only about improving my solution. And as we will see today, that there are actually many variants of the probabilistic roadmap, because you can always choose how you sample points. There's also a choice of how you compute neighbors. And finally, there's also a choice of how you compute feasible paths for edges between configurations in your roadmap. And in the end, we will also see that the result is very often in the same homomorphism class. So basically, you can always transform your solution into an optimal solution, but usually they're very far away from being optimal. And so usually what you do in practice is that you also employ some path smoothing. And so this is something which we will see a lot more in the lecture, that sampling-based planning is actually pretty efficient, but the paths which you get out of them in the end, they are very often having this zigzag motion, and so this is usually a bit, not optimal to execute, and sometimes also, very inefficient, and it also looks pretty bad to have paths which are not super smooth. Okay, so this is just again a general overview about PRM, and now I want to go a little bit more into details about how you sample, how you compute your neighbors, and also how you do the feasible path computation. Before I do that, any questions about this general idea of probabilistic roadmaps? Okay, cool. Then let me go to the topic of sampling for probabilistic roadmaps. So the way we do that is usually that we employ rejection sampling. So the idea is that we are sampling some configurations from our configuration space given from some distribution. And then we repeat sampling until we actually find one configuration where the body of the robot is in the free workspace of our environment. And we write this here as B of Q, which is the body basically at the configuration Q. It's a subset of the free workspace. Sometimes you also write this as Q element of Q3, which is basically just the free configuration space. So those both are equivalent. And the nice thing about rejection sampling is, of course, that you don't need to explicitly define your free configuration space. There are actually some people who try to do that, but it's super difficult to do. And usually you can't really explicitly represent a configuration space in more than, let's say, 3 or 4 dimensions. It gets very complicated very quickly. And so that is why this rejection sampling has turned out to be one of the most efficient ways of actually solving motion planning problems. One caveat which you have to keep in mind is that rejection sampling usually is pretty inefficient in highly constrained spaces. And so the reason is, of course, that if you have a very large configuration space and you have maybe a very small door or something or a bottleneck in your configuration space, then usually just by sampling you will not hit exactly the spot where you actually have to find a configuration to solve the problem. Yeah, you can also see this, for example, in this room. When you want to go out of this room, you have only the position here of the door, and for finding a motion, you have to actually find a configuration which is exactly at the door, and if you just sample randomly, you will very rarely actually hit this exact spot where the door is to actually solve the problem. And so this is often one of the main problems in sampling-based planning, that you have to wait a long time until you find this one configuration which is actually the one you need to solve the problem. And a lot of research also goes into the direction of finding out how you can direct sampling a bit more into the direction of finding those very constrained and narrow passages in your configuration space to solve them. And common choices for a distribution are uniform distribution, Gaussian distributions, and also something we will look at are deterministic sequences. Okay, so let's look at some examples. For example, if you have a small car robot here and you have a configuration, let's say, of x, y, and theta, whereby theta is the angle of this car robot, then you can see that all those components are independent, and if you want to sample, you can just sample all components independently. So here are 3 different uniform distributions from which you can sample, and that gives you a good cover of your configuration space, and the resulting state Q will be still drawn from a uniform distribution. So basically, if you want to have uniform distributions, you can just do uniform sampling in each of the dimensions and then combine them to get uniform sampling on the whole configuration space. If you have actually orientations or rotations in 3D, then things are a bit more complicated. So if you actually, so SO3, I think if you remember from the second lecture, it's basically the orientation of a rigid body in 3D space. And one way to represent this is by using Euler angles. And if you want to sample that, then one idea you might have is that you sample Euler angles uniformly between 0 and 2 pi, for example. You construct a rotation matrix, and then you use that to actually sample orientations. But this is a bit tricky because this is not uniform, and the reason is that Euler angles are usually not independent. And so if you, for example, visualize this, one way is to visualize this on a sphere. So each point here is your angle and pitch is represented here by the rotation of those needles here. And if you just do uniform sampling of the Euler angles, you will usually get something like that, where a lot of points are clustered around one of the poles. Does anyone know why there is actually a cluster when you do uniform sampling with Euler angles? Yes.
Because I have 2 ways of sort of getting to the pole, so I can just maybe just pitch up 90 degrees, or I can rotate 90 degrees and then pitch downwards and end up at the same point.
Yeah, exactly. So there are basically multiple ways to get there, and by just uniform sampling, you will have a tendency to sample more in this direction. Right. So, and to tackle this problem, there's actually a better way to do it by using quaternion. So I don't want to go too much into details about quaternions, but the idea here is that you represent SO3 by 4 numbers, and those 4 numbers are points on a unit sphere in 4D space. And if you do that, you can actually show that you can very nicely and very uniformly cover all the rotations. and you avoid this trap of having too many configurations at the poles. And the way of how you do that is that you sample 3 points from a uniform distribution, then you compute those formulas here, you get those 4 points on the unit sphere, and this is basically your representation of a rotation, and then you can convert from here, for example, back to Euler angles, back to a rotation matrix, and you can use that to actually rotate your robot into the right direction. Yeah, if you want to know more about this, there's a nice expose in the Laval book about planning algorithms. Yeah, but this is basically the de facto standard of how you can sample efficiently and uniformly from rotations in 3D space. Okay, another idea I want to show you are deterministic samplers. And one of the most important deterministic samplers is the Halton sampler or the Halton sequence. This was invented in 1960. And this gives you a better, I would say, uniformity compared to pseudo-random numbers. And it is also incremental. And so here is an example of how the Halton sequence would sample a line segment. So the idea is basically that instead of just randomly picking a point on the line, you first pick a point which divides this line into half. And then you pick next points which divides the remaining segments again in half, and so on and so on. And so, yeah, the cool thing about that is, of course, that instead of maybe getting a lot of points at a certain locations, which you got usually with pseudo-random numbers, you get here really points which first explore the space very broadly, and then they go into details later on. And so you see here already with like 7 numbers or so, you have a nice covering of the space. And if you need like a denser covering, you can add more and more and more points. But the cool thing is, of course, that you have already a good covering in the beginning. And there are different ways of how you can employ this Halton sequence. You can either subdivide your line segment here into 2, but there are also approaches where you can just divide it by 3, and you get 3 line segments, and you can again put points here by again subdividing it into 3 and adding points there. So different ways of how you can do that, and the pseudocode to generate exactly this behavior of like subdividing or dividing the space into certain parts and then getting samples from there. This pseudocode here is shown here. So what you need as input to a Halton sequence is a number p, which is the base. So that could be, for example, 2 if you want to subdivide by 2. And you need to give it a number I. And so this number is basically just, if you want to sample, you go from 1, 2, 3, 4, 5, and so on. And the more you get, so the bigger the number grows, the more you actually subdivide your line segment into smaller parts. And so I want to just go over this code here once for one particular query. So let's say you have as your base 2 and you have as your number I6. So you want to have the 6th number from the Halton sequence. How this actually works is that you have a number h here, which represents the output. You have a number j here, which represents the running remainder of the number which you have as input. And you have f here, which is the current fraction which you employ. And then you just iterate here. So for example, for our case of 2 and 6, you start with h is 0, j is 6, and f is 1 divided by 2. Then you go here into this loop. You compute j divided by p, which is basically the fraction you get here for the base. You get a quotient and a reminder of this computation. So in this case here, you have q is 3, r is 0. And then you go on and you update your h. H is 0 in this case. You update j, which becomes 3, and you also update f, which is 1 divided by 4. So you can see here f is always increasing into the fractions. So you go from 1 divided by 2 to 1 divided by 4, and then 1 divided by 8, and so on. And the higher the numbers are, of course, the more you actually go down into the fractions, and the more you get more denser values and not just subdivided values. So let me just continue here. So we have the first iteration where h is 0, and then in the next iteration you have j is equal to 3. You divide 3 by 2. You get here as q1, and the remainder is also 1. You update your h. H becomes 1 divided by 4. You update your f and your j, which becomes 1 and 1 divided by 8. And then you go to the last iteration. You compute, again, j divided by p. You get q0, r1. H becomes 1 divided by 4 plus 1 divided by 8. You update your j, which becomes 0. And you also update your f, which becomes 1 divided by 16. And then in the end, you are done because j is 0, and your output is 3 divided by 8. And one nice thing you can note about this, so the sixth number here in base 10 is actually 110 in base 2. And 3 divided by 8 can actually be written as the inversion of 110 times all the fractions. So, and as you can see from this example, the higher actually your number goes, the more, the larger also some binary number grows, and the more you actually use also the other fractions which you have not used in the beginning. So for smaller numbers, you only use like the first fractions, which corresponds to just subdividing once or twice. And then the higher the number actually grows, the more you subdivide and subdivide and subdivide. And you can do that not only with base 2, you can also do that with base 3 or any other prime number. And so that is basically a very efficient way of generating this deterministic sequence and creating something which is a bit more structured compared to like pseudo random numbers. Okay, so let me give you just an example sequence. So for base 2, the first 7 numbers would be 1 divided by 2, 1 divided by 4, 3 divided by 4. Those would be equivalent to just subdividing and then again subdividing the remaining line segments. And then again you get the higher fractions here divided by 8, which corresponds to, again, subdividing the remaining segments. The way you can actually use the Salton sequence in higher dimensional spaces is by using different prime numbers per dimension. So for example, for a 2-dimensional space, you can use prime numbers 2 and 3 for x and y. And that gives you usually a very nice representation of deterministic sequences. Okay, and here is a small example of how this could look like on a 2D grid. And the question for you is, which one is actually the pseudo-random uniform sampler and which one is this Horton, this deterministic sequence? Anyone an idea?
The left one is Horton.
Why?
Because it's more uniform distributed, more average on the space.
Yeah, that is true. I would say one really bad property of pseudo-random numbers is that you have this clustering. So for example, if you look at this picture here, you see a lot of points are here, maybe a lot of points are here, but then there are larger areas where you don't have any points. And so this is usually something which we don't want to have for motion planning because we want to have something which covers the space really uniformly and doesn't discriminate against some of the regions. And so that is the biggest difference here, that the Halton really generates this nice grid-like structure where you get a lot less free workspace and you don't get this clustering. Okay, and we talked a little bit about, or you said that it's more uniform, and there's actually a better name for that, namely the name of dispersion. So what is dispersion? Dispersion is basically that if you have a configuration space Q and you have a set of points P in this configuration space with a metric D, then the dispersion is actually defined as the maximum distance from any configuration in your configuration space to the nearest sample in your set of points P. So basically, you go over all possible points in your configuration space and you compute the minimum distance to the nearest point, and the dispersion is just the maximum of all of that. So what does it mean? It means basically that you want to find out what is the point which is farthest away from any point in your current set of points. Here's a small example for this uniform sampled space which we had before. If you have a Euclidean distance and you compute the dispersion, then you want to find out basically what is the circle or the disk with the biggest radius, which is still inside of the configuration space, but which is not touching any of the points. And the bigger this becomes, the bigger is your dispersion. And of course, minimizing dispersion is a very good measure of how well your sampling sequence is actually working. And this is not only working with like the Euclidean distance metric, but you can also use L1 here, this box-like distance metric, where all the points on the box here are equally far apart from the center point. But you see, regardless of the metric, you get pretty similar results. And you can, of course, use this measure here to make really an informative or a quantitative statement about how well you have actually covered your space. And you can also make a quantitative statement about how well your sampling sequence works for a particular configuration space with a particular metric. Okay, then the minimal dispersion which you can actually reach if you really go to the limit is that you create a grid. And for this example here, where you have, I think, 36 points, if you compute the dispersion, you get 1 divided by 12, which is basically just the radius of a circle, for example, at one of the cross points here, which is still inside of the configuration space, but not touching any of the points here in the grid. So the best way of how you can minimize dispersion is to get a grid structure. And that brings us to the question of why would we not use a grid for sampling? And maybe one of you has an idea. Yes?
Because we always get the same results. For example, if we try to find the door and the grid is not in the door space, we will always get no solution. If we do probabilistic sampling, we are guaranteed to, at some point, get a solution because we will find a sample in the doorway.
That is true, but couldn't you just increase the density of your grid, make your grid finer and finer and finer? Yeah.
You can, but then your search will like get more and more complex, and it doesn't really scale well.
Yeah. I would say what you said definitely correct, but the scaling aspect is actually the one which is really breaking things, especially if you go up to higher dimensions. Yeah, you can just maybe do this as an exercise. You can compute how many points would you need in a 10-dimensional space. If you cover one of the dimensions with, say, 10 configurations, you will see that this scales already pretty quickly to numbers which are, yeah, all the atoms in the universe or something, which means it's just not practical to go to really high dimensions with that. And another one which is important is that a grid is not incremental. So if you actually change the resolution of your grid, it usually requires exponentially many additional points. And so here's an example. We have started with 4 points, and maybe we don't have a solution. And one way of how you can overcome this is making the grid smaller, just adding one more step here in the grid. But if you do this, then yeah, going from 4 points, which you had initially, and you have a dimension of 2 here, then you get to the next point of 36 configurations if you want to keep the structure of the grid. And so this is bad already for 2 dimensions, but if you go for 4, 5, 6, then it becomes so bad that it's usually unusable to use this for real motion planning problems. Okay, and here a little comparison between the ones which we looked at. So uniform grids, random sampling, Halton sequences. One measure which we can define on them is this dispersion, which I talked about. So we get here the different dispersion values for Halton sequences, random sampling, and uniform grids. And you can see that uniform grids, for example, they have the lowest dispersion, but they are not incremental. You can't just add one more point. You need to really subdivide the grid again to get more points. For random sampling and also Halton sequences, this is incremental. You can always add one more point. Another thing which is interesting to know if they are actually having a lattice structure. So a lattice structure means that you can represent any point from your samples by a combination of 2 other points from your sample set. So in a grid, you can always take 2 points and you can just add them to get to a next point, but you can't do that in a random sampling. But for Halton sequences, you get this property again. Also, this is a bit more complicated to actually do. And yeah, if you have this lattice property, one thing which is nice is that you can also compute the neighbors directly. So you could, for example, take a sample and you could already store the neighbors of the sample in this configuration. Okay, so I would say this is all for what I wanted to talk about sampling for probabilistic roadmaps. Does anyone have questions about this part? Yes.
I found that it's like useful to scale the samples based on basically the inverse kinematics. So if you have a robot arm, like some links are longer and some are shorter. Like how would you implement this properly that you like basically sample a bit based on how the movement is actually in the Cartesian space?
Yeah, so I would say for every scenario, you can always come up with better ways to do something. And I mean, you've talked about a very special case where you have a manipulator robot and you can compute inverse kinematics. Very often you maybe have just a car robot or you have a different kind of robot, so you can't do that. But yeah, in your case, it could make sense. But yeah, what you see in practice is that, first of all, inverse kinematics is super expensive to compute. So usually it's way faster to just sample random points and then just brute forcing your way to the solution. And second is that also it's very difficult to find the right points in your workspace. So if you just randomly sample points, then sometimes you get points where you don't have an inverse kinematic solution, so you just wasted time doing this very expensive computation without getting anything. While if you just sample joint configurations, you're always sure that you have a solution for your robot. And so you have to be a bit more careful there. But for example, if you want to just, I don't know, paint something on a wall and you know your robot is very close by, then of course it makes sense to just sample points on your wall, compute inverse kinematics, because you know that there are solutions there. So yeah, there's not one answer to this. It really depends on what you want to accomplish, but usually I would say it's more efficient to just compute joint values, get a solution, instead of going the other way around.
But would you, for example, like on an arm, would you increase the density on like the base joint because it has, I don't know, one degree is like 20 centimeters, and on the end effector link it's just like 1 centimeter.
Yeah, so this is also something which people do, makes a lot of sense. Sometimes you can also run into problems with that. For example, if you, I don't know, need to put a key into a keychain or something to open the door or so, then sometimes you need to like sample a lot of points actually at the last joint of your robot, and then you would actually need to put more samples there instead of like sampling in the base joint, which would, yeah, jump very far away from the goal, for example. It always depends on what you want to accomplish. So yeah, there's not like one thing which I can tell you that it makes always sense to sample more the shoulder, but of course there are certain situations where this definitely makes sense and you definitely should do this. And yeah, I think this is also implemented in this open motion planning library, which we'll look at later on. So people use this, and this is definitely useful. Okay, any other questions? Okay, next topic, nearest neighbor computation. So nearest neighbor computation is actually the second big module which you need in a probabilistic roadmap. And usually you want to have an efficient nearest neighbor computation module which has the following interface. You need to be able to add configurations to it, to some kind of underlying data structure. And then what we want is actually two functions. One is called query k, one is called query r. And this function, query k, it returns you the k nearest neighbors with respect to a distance function, of course, of configurations which you have added to the underlying data structure. And the second one, query r, is basically very similar, but instead of having k nearest neighbors, you want to have all the neighbors which are in a given distance radius r of your configuration queue. So those are the two functions which we want. And internally, one of the best data structures to accomplish this is a balanced binary search tree. So here we have an example where we have a tree and all the leaf nodes are points. And you can imagine those points being points on the number line from 0 to 100. And all those points here have been added in a previous iteration to this tree. And all the leaf nodes, they represent really the samples, and all the non-leaf nodes, they represent a value, and this value is always greater or equal to all the values in the left subtree and always smaller than all the values in the right subtree. So for example, if you have a 23 here, then you know that the largest value in this subtree here is 23, and you know that all the values in the right subtree, they are always strictly larger than 23. And if you now want to find like some range of points, for example, let's say between 25 and 90, then you can just go and query the search tree by going always left if your number is smaller than the number here, and going right if it's bigger. So for example, if we want to have 25, then we look, okay, it's smaller than 49, it's bigger than 23, smaller than 37, smaller than 30, and you end up here in this leaf node of 30. And you can do the same for another number. For example, for 90, you see here it's bigger than 49, bigger than 80, bigger than 89, smaller than 93. And you get to 93 leaf node. And by doing that, you can now color the nodes into 3 colors. So white means that those points or those samples, they are outside of your range. Then you have your black points, which are all the samples which are inside of your range. And then you have the gray points here, which are samples where you are unsure if they are currently inside of your range or outside. Okay, and to build such a binary search tree of n numbers, you need a time complexity of n log n and a space complexity of O of n. And to find an entry, it's pretty efficient. You can do that in O log n time. And if you want to have a range of k numbers, you usually end up with a query time of O log n plus k, whereby k is the unknown number of samples you want to find. And the question for you is, what would be the naive range query time complexity? That would be basically the time complexity if you don't use one of those specialized data structures. Any idea? Yes.
O of n?
Yeah, that's true. So basically you have to consider all n numbers. You have to check if they're inside of your range. And that, of course, gives you worst case complexity of O of n. OK, and the same idea of this balanced search tree can also be extended to multidimensional data. So for example, for the 2D case, we usually use something which is called a KD tree. And the idea for the 2D case is that you split your point set alternatively by the x coordinate and by the y coordinate. And splitting by x coordinate basically means that you split by a vertical line, so that half of the points are left or on this line and half of the points are to the right. And splitting by y coordinate means that you have a horizontal line and you split the points half below or on it and half above it. And here is an example of how this KD tree would work in a 2D example. So you have the leaf nodes. Those are all your points again. So for example, here we have a 2D grid. We have 10 samples. And then all the non-leaf nodes, they are basically lines which you have drawn into the grid to subdivide it. So in the beginning here, you have written one line, L1, and this L1 line is really the middle of the point. So half of the points are either to the left or on the line, and half of the points are to the right. And then once you have subdivided it by L1, you subdivide it again by L2 and L3. Those are the horizontal lines here, L2 and L3. They again subdivide the space into all the points which are half of them below or on and half above. And the same here for L2. And then you do that recursively until you have only one point in each of those small boxes here. OK, and here is some pseudocode of how you do that, basically exactly of how I just explained it. So you can build this KD tree by having all the points which you currently have on your grid or in your configuration space. And you start here with the depth. And the depth is in the beginning 0. And then if P only contains one point, then you return a leaf node storing this point. And then else, if the depth is even, then you split your point set with a vertical line through the median x coordinate, so that basically half the points are left, half the points are right. And if it's not even, then you split it with a horizontal line. Again, half the points are above, half the points are below. And that gives you basically two subsets of points. For each of the subsets, you can build another KD tree recursively by increasing the depth here and just operating on the subset. This gives you two new nodes, left and right. And so in the end, you create a new node V where you store the line which you have just created, plus making V left and V right the child of V, and then just returning V. And that is basically the general recipe of how you can construct this KD tree in a recursive manner. And yeah, one important thing for computational purposes is that regions can either be explicitly stored at every node or computed on the fly while you traverse from the root. So either you have already a region operator where you have all the subsets of points stored and you represent them in each of the nodes here, or you don't do that and you do that basically on the fly while traversing from the root. Okay, that is how you build this. And now we want to look at how you can query this KD tree. And for that one, let's look at this example here. We have a grid with a bunch of points. We have constructed this KD tree, and you have a bunch of vertical and horizontal lines from the KD tree. And now let's say we have sampled a point here, which is this light blue. And we want to know what are actually the nearest neighbors of this point on this grid, given this KD tree which you have just constructed. And the way of how you do that is that you start and you check if this new point is left or right of the first vertical line. And in this case here, it's on the right. Then you check again if it's above or below the next line, and so on, until you actually get to a leaf node where you have just a region with some points in it. And in this case here, you compute the distance between all the points in this leaf node and the query point. And this gives you the nearest point plus a distance, a minimum distance to this point. And of course, this minimum distance might not be the overall minimum distance. So you basically can just draw a circle here. This is basically the minimum distance to the point here in this region. And what we need to make sure is that there's no other point in this region here which has a closer distance. If it does, then we have to change it somehow. And you can see already here there are a lot of points inside of the circle. So basically you have to change, and the way of how you do that is that you backtrack. You basically look at the nearest subtree here. You check, are there points in one of those leaf nodes which are closer, and you compute here for the first leaf node all the points, all the distances, and you can see here you can update the minimum distance to one of the points here which is very close to our query point. And this gives you an updated distance, and this updated distance you can use to actually prune other areas of your tree. So for example, in this case here, you don't need to compute, again, the distances to the next leaf node here, because the distance is already outside of the new computed distance. You can also check this again for the next subtree further up, and you can do that for the root again, and then you end up with those two regions which contain the nearest points, and one of them is the nearest point to our current query point. Right, and in this way you basically just prune the search area based on region bounds and distance bounds, and this is basically one of the most efficient ways of finding the nearest neighbor also in higher dimensional spaces. Okay, some practical notes about KD trees. Yeah, first of all, they are much faster than a naive implementation, and if you actually go to higher dimensions, then the time complexity becomes O of n to the power of 1 minus 1 divided by d. You have to just believe me this number for now, so I don't want to go into proving something here. Plus k. K is the number of unknown points you want to find. And it turns out that this is actually not super efficient in high dimensional space, so you can do it, but it's not really the best one. And so there are some other algorithms, for example, approximate nearest neighbor algorithms, which can help. But if you do that, then you might get rid of some of the theoretical implication, of the theoretical properties, for example, of probabilistic roadmap planners. And so you have to be a bit careful of doing that. So it's always a trade-off between having nice guarantees and having very efficient algorithms. Yeah, and it's also possible to support more complicated configuration spaces. So for example, you can also use KD trees on SE3. And one question which is left is, can you also use KD trees incrementally? And the answer is yes, but you have to be a bit careful there. So one way of how you can do that is that you reconstruct the tree only every 1,000 nodes or so, because yeah, reconstructing the tree is actually pretty expensive, and usually you don't want to reconstruct the tree every time you add a new sample. And so one way of how you can make this work in practice is that you only do this every 1,000 nodes, and in the meantime you have a list of samples which you have not yet added to the tree. And so when you want to query, then you first search the KD tree and afterwards the list, and then you take just the minimum over both data structures. And so this is usually a more efficient way of how you can actually avoid doing the KD tree generation every single iteration. Okay, any questions about nearest neighbors or KD trees? Yeah, please.
I was wondering if this sorting is, like, how do you do it if you're, for example, sampling the angles of joins? Because
The what?
if you're sampling for the angles of joins,
Mm-hmm.
because then I think the configuration space is a torus, so you can go around and around.
Mm-hmm.
And how would you do this sorting then in the tree by axis dividing?
Oh, so yeah, this axis dividing is really just for a 2D configuration space, which is an Euclidean configuration space. And so, of course, you would need a different strategy if you have a more complicated configuration space, especially one where you would go around. Yes?
Do you know why we're using KD trees and not maybe like axis-aligned trees like octrees or something?
Mm-hmm.
Is there disadvantages and advantages between these two?
So I'm pretty sure that people have tried both of them, and I think there are definitely also implementation of that one. But yeah, the answer is, of course, because it works in the most efficient way, and none of the other algorithms has better results. And so this is usually, how you can.
Okay.
Yeah. But yeah, good question. So I mean, so from the start, you don't see any big difference between them. But if you evaluate it and you try it out on different scenarios and configuration spaces, and suddenly you see that one of them is working better. I can't tell you right now why this one is working better, but usually you have to just go with the one which works best.
Yeah.
Okay, any other question? Yes.
Can we also use this for sampling, like directly sample from like a random region so that we don't have to do like the full querying?
From a random what?
From a random sub-region,
Mm-hmm.
so that we don't have to do the full querying. I don't see where this is needed.
So you want to use the KD tree directly for sampling?
Yeah, basically select a random region and sample from it. Then we don't have to do the querying, like the full querying.
Yeah, so theoretically this is definitely possible. But I don't know if you then still can keep this uniform sampling property. Because this KD tree, it could have not enough samples right now. And so, for example, you want to really have this one sample which is maybe at the door so that you can leave the room. And if you only sample in those regions which you have right now, they might not find very quickly this one configuration. And instead, you would just sample around your current graph. This might make sense in some cases, but very often you want to just sample broadly so that you find this one configuration which could directly solve your problem. So, but yeah, it's always a trade-off, and I would say, so I think next week we'll also look at a tree-based planner where you where you try to expand this tree into different directions, and there definitely makes sense to, for example, sample in this way. Okay. More questions? Cool. Okay, then let's move on. And let's revisit again the probabilistic roadmap. This is a pseudocode which I showed you in the beginning. And what we looked at were two functions. One was a sample function. How do you actually sample from the configuration space in a manner where you can have some uniform distribution and where you don't cluster points, for example. And then we also looked at how you can store the vertices in an efficient way and how you can query them to get neighbor points so that you can connect each of the points here to the neighbors which are in the roadmap. And now I also want to look at a third computation, namely the one where we want to check if the path from Q to P is feasible. And that is basically important to check if this edge here, for example, is in the free workspace. And we already saw of how you can sample, of how you can check collisions, I think in the second lecture. But I just want to revisit this again. So one way of what we looked at was that we had this flexible collision library which can do collision checking, and something which it can also do is continuous collision checking. So this is basically the idea of checking directly if an edge is valid. So basically multiple points of a robot instead of just checking if one configuration is valid. And this works pretty well as long as the motion is a linear interpolation. And if you can't do this continuous collision checking, then the alternative is basically that you just compute intermediate configurations during the motion, and then you have to check the collision for each of the intermediate configurations. And of course, this is significantly slower than continuous collision checking. But it turns out that in practice, usually this one is used because for continuous collision checking, you need to do a lot more work to get it to run, especially on specific samples. And I think this one is a very general way of how you can solve it, and you don't have to know a lot about your robot or your environment. You can basically do that for any kind of robot, any kind of configuration space, any kind of environment. And one thing which you have to keep in mind is that the output of PRM is often pretty far from optimal. And that is why usually we need to really post-process the data once you have found a path. And I guess one of the most obvious and actually pretty well working things you can do is path shortening. So let's say you have found a path on your roadmap and you have a number of waypoints here of vertices, Q1, Q2 until Qn. And you can shorten this path by just picking Qi or Qj randomly and then checking if they can be connected by a line. And then replace this path between Qi, Qj using the line. And this basically just shortens your path and makes it more optimal with respect to shortest path, of course. And in practice, I would say you do a bit more sophisticated way of doing this. So instead of just choosing the vertices, instead you take the whole path, and the whole path could be like the zigzag motion here. And then you pick 2 points on the path, for example, here and here, and you check if the edge between those points is actually in your valid workspace. And if it's not in the valid workspace, then you discard it. And if it is actually in your free workspace, then you add it to your path. And in this way, you can successively shorten the path. So you pick, again, in the next iteration, 2 points. You try to connect them. You get a shorter path, and you do that, and so on, until you converge or you can't find any more valid connections here. So in practice, usually you would add some more computations here, because usually if you do this path shortening, you will see that in the end you get a lot of points on the path, and then this path shortening operation gets pretty expensive. And so usually you try to also collapse vertices which are very close together. For example, if you have 3 vertices here, sometimes it actually makes sense to just combine them into one. And so this makes the whole computation a bit more efficient. Okay. So let's look a little bit at theoretical properties. I think we will go more into details in one of the next lectures, but let's just analyze this a little bit. The probabilistic roadmap has actually a very nice property, namely that it is probabilistically complete. And this means that it is guaranteed to find a solution if a solution exists. But it is only probabilistically complete, which means that this is only true in the limit of the number of samples going to infinity. So if time goes to infinity, then you can actually prove that with a probabilistic roadmap, you will actually find a motion if one motion exists. And so this is a milder form of this general property of completeness, which we'll also look at later on. And in terms of convergence, there are actually no guarantees, so this is not super helpful in practice. But I think this probabilistic completeness plus that sampling-based planning works pretty well in high-dimensional spaces makes probabilistic roadmaps actually one of the most important algorithms for motion planning. And having this property here is actually already a very nice achievement, because if you don't have it, then of course you can have cases where there's a solution, but you will not find the solution. And here at least you have this guarantee that the more time you spend, the more samples you draw, the more you can be sure that you at some point will actually reach the solution. And on the contrary, this also means that if there's no solution, then this algorithm will just never stop and just run indefinitely. Okay, any more questions to theoretical properties or PRMs? Exactly, yeah.
We probably discuss this also a bit later, right? Like about the properties, because otherwise, like how do you choose the steps and like this kind of stuff? Like,
Mm-hmm.
do you have some guidance on that?
So there's no general recipe of how you actually choose this. So this is really something which you have to try out and practice. There are some theoretical works which try to find out what is actually the minimal distance of a configuration of the robot at a certain configuration to the environment. And if you know what is actually the distance, then you can make some educated guesses of how small actually your steps need to be to really make sure that you are exact, that you are telling me that it's in collision if it's actually in collision. If that makes sense. But yeah, usually it's pretty difficult to actually compute this, and I think it's only possible for fixed space manipulators, as far as I know. And some smaller robots, of course, like a car or so. And in those cases, you can actually make a statement about that you can now stop sampling because you know that it is not in collision. But usually you have to just subdivide it and subdivide it super fine until you are roughly sure that it's so close together that there is no collision possible anymore.
But isn't that like the most computationally expensive part, like the collision checking in the end? That you really have to try to reduce that as much as possible.
Yeah, exactly. So that is why there are actually some approaches which, for example, do some kind of lazy collision checking, where, for example, they only check in the end when you found a path, if this path is in collision or not, or where you just do like some approximate collision checking, where you just do some discretization of each of the edges, and you check if it's okay, and if it's okay, you go on, and in the end, you do another very, very finely grained collision checking to really make sure that the final path is collision-free. And if it's not, then you can always like backtrack, throw edges away, and do the computation again and again. But yeah, this is a very good point. So a lot of research in this area actually went into efficient collision checking and how you can make it better. And yeah, so this lazy collision checking is, I think, one of the most important ideas in this direction. Yeah. Okay, any other question? Cool. That was actually everything for today. Just to conclude, so what we talked about were probabilistic roadmap planners. And probabilistic roadmap planners are something which we call multi-query planners, because you can construct roadmap once, and then you can reuse it for different start and goal positions, as long as your obstacles don't change, your environment doesn't change, your robots doesn't change. And so this is a very nice property. And so, for example, if you're in a factory or something and you have a pre-computed roadmap, which you can reuse for different start and goal configurations, so this is a very nice property. And this is why probabilistic roadmaps are used a lot in practice. We also talked about KD trees, because they allow very fast neighbor computation, which you really need for this kind of algorithm. And I would say this whole probabilistic roadmap approach is super simple in the beginning, but if you go into details, you find out that there are a lot of difficult questions and a lot of trade-offs you have to do to actually make this work. One was this choice of sampling. Then, of course, this choice of nearest neighbor computation. So KD trees work pretty well, but sometimes you have scenarios where this is not working very well, and then the question is, what do you do? And of course, handling of metric spaces is also an important thing which we didn't talk about. But of course, sometimes if you have very weird metric spaces, then For example, KD trees can maybe not be applied. You have to also keep this in mind. Okay, and next time we will look at the second biggest tree-based motion planner, which is called the Rapidly Exploring Random Tree. And I would say probabilistic roadmaps and this randomly exploring random tree, they are basically the two most important algorithms for motion planning, and I think also the ones most used and also the ones which most of the modern algorithms are based upon. And we will also look at optimizing planners. That is basically planners which guarantee you that they will not only find a solution, but they will find you the global optimal solution to a problem, so they will find you the best motion which is possible under an optimization objective. And that is everything for today. And in the end of the lecture, you can also find some more references to what we talked about today. All right. Thank you very much.